bags are the same. Okay, so today we're going to talk about gunshot residue. We're in the third part of the course, which is more the physical evidence. So, this would be primer strikes and ballistics and so on, but there's still some chemical information in all of these things. So as chemists, we would be sort of studying the trace residues or chemical properties of physical evidence, okay? It's not really pattern evidence. We're not going to be talking about comparison microscope analysis of rifling marks on bullets. I mean, that would be more criminalistics, but we will talk about some of the physical evidence that we get as evidence for crime. So what I've got in the bags going around is some different cartridges. You can look at the backs of the cartridges here to see, I'll show you on the video, show you the calibers of these things. These are from some of the, these are from my personal stock of ammo, I guess you could say. This is a 40 caliber, this is a 380. So these would be, again, more, they're pistol rounds. This is called a cartridge, not a bullet. The thing on the end of the round is a bullet, okay? This is a cartridge. The cartridge contains, and we'll see on the next slide, the powder, the primer, and everything. Now, if you look in those bags, maybe you saw it. You saw this little can here. Let me show the video. This little can. You can see on the end is a primer. This is a primer can and a shotgun shell. So the primary explosive is inside this. It's really not an explosive. It's a shock-sensitive propellant. So it generates hot gas and sparks, and that will go in and light the gunpowder. So that's what the primer strike is, that little indentation. And that's one of the physical pieces of evidence that you can see is the firing pin. So you can get on a microscope and look at this little indentation, and you might see some imperfection in the firing pin. Maybe it's got a little, off-centered nature to it or a scratch on it. And then you can see if the, spent cartridges that you find at the scene all have the same primer strike and they have the same firing pin shape, then you can tie it to that weapon. It's not 100% accurate, but if there's a really obvious defect, then you could say, yes, this is consistent with that firing pin. I put a 22 long rifle shell in there, probably the most common hobbyist round. So you see this tiny little thing. Now on this shell, notice you don't see a primer cartridge in the bottom. This is called a rimfire round. And so if you look at that rim is not just brass. There's a little, like a little cavity around that rim. And on the inside, they have the primer inside the rim. And so for 22 long rifle rounds, they strike that rim, and then that sets off the primer. It sets off the gunpowder, produces the pressurized gases that propel the bullet through the barrel. Got a couple of shotgun rounds in the bags. This is a 20 gauge round. This is a 12 gauge round. Notice the larger the number, the smaller the diameter. So it's kind of strange. In these cartridges, the bigger the number, the bigger the diameter. So on calibers, like a 40 caliber or a 270 caliber, those are thousandths of an inch. Okay, so 0.3 would be a 30 caliber, 0.4 would be a 40 caliber, 0.45 would be 45 caliber, and those are 0.45 inches. Okay, this is a 380 round, so 0.380. This is a 40, so 0.4 inches. So those, again, the bigger the number, the bigger the round. For shotgun shells, it's kind of like a denominator. Gauge is like a denominator. So think about in the old days, if you had a pot of lead, you had a pound of lead, how many bullets could you make, right? Say if it's 12 gauge, you can make 12 bullets out of that pound. If it was 20 gauge, you can make 20 bullets out of that pound. So the gauge, the bigger the number, the smaller the round. Because you can think about it, I can get so many bullets out of this stock of lead. Okay, so that's how the gauges work. So you can see up here, I've shown you've heard of maybe AK-47 or AK platforms, and you may have heard of AR platforms. And so those are the two rounds. This little gray cartridge that's in your package, that's a 223 or AR or 5.56 millimeters, 5.56 millimeters. And so that's the round that's shot in those military-looking guns. This is from my 270 deer rifle. So look at the comparison of those. Now, what's the difference? It's not that much difference in the size of the bullet. I mean, the bullet is bigger for sure. The diameter of the bullet, this one's 0.223 inches. This is 0.270 inches. So not that much difference in diameter. Length of the bullet is different. This is a heavier round. It's definitely more destructive in terms of taking down a larger animal. And so the deer rifle, this also has kind of a hollow point nature to it and a whole lot more powder. So this round is going to go a lot faster and a lot farther and shoot flatter. Okay. There's, in the little pistol rounds, you see the end is hollowed out. Okay, that's called a hollow point. This one is more of a blunt round, and you can see that it's what they call full metal jacket. So the lead is completely enclosed in a copper, non-corrosive, non-toxic jacket. So you might hear a FMJ, that's full metal jacket. Those are, a lot of times those are sold as target rounds because they're cheap. They don't really, you're not interested in imparting all of the energy into what you're shooting. Now, I mean, we're talking some, pretty sobering discussion when you're talking about trying to put all of the energy of a bullet into the thing or person that you're trying to shoot. Let's take a scenario where you're on an airplane and you're wanting to take out the bad guy in an enclosed tube. And you don't want the bullet to go through the person, right? Because there's passengers on the other side of that person. And so that's the ideal scenario where you want all of that bullet energy to go into that person and not go through that person to get someone else, okay? Of course, with that scenario, then you also have the bad use of that technology. But yeah, the hollow point or these critical defense rounds that have like a plastic bead inside the hollow point, it may even be a shape that produces a point so it's more accurate, but yet it's a plastic insert. It's still the lead will hit and mushroom out and slow down in the body and deliver all of the energy into the body. So a lot of those rounds were engineered for air marshals, that kind of scenario. And so, like I said, it's sobering to discuss. So this is a range of common calibers. Now, over on the far right is the 50 BMG, which is the 50 caliber gun, a sniper rifle or machine gun. Sometimes they're set up into the machine gun arrangement. And that's not to scale. That thing it's a little longer than this even. There's so much powder in that thing. So you can go on the Forensic Chem website and look at the playlist area, and you can see some of the different videos that we have with people shooting different size rounds and looking also at detecting gunshot residue. Here's sort of a breakdown of the cartridge. So this is a hollow point round. You can see this is a cutaway, and so you can see that hollow part right here. Right here. So this has been hollowed out. So when this enters whatever it's being shot at, it causes this to mushroom out and create a larger hole, if you will. Okay. This is the propellant. I mean, we call it gunpowder, but it's not your grandpa's gunpowder. This is well-engineered, polymer-bound gunpowder. It's the really small prills. It's not just some random powder dumped into a little case. They're little pressed pellets, kind of through a micro sausage grinder. Like they make this slurry and they squeeze it through, and all the little prills break off. So they have a pretty well characterized surface area, so that they burn at a certain rate. You want them to burn mostly inside the rifle, so it generates the most pressure or the pistol. So it generates the most pressure to get that bullet out as fast as possible. This is the primer over here, and inside this is that lead stiffenate most commonly. So it's shock sensitive. So the firing pin hits that piece, and then that causes it to catch on fire. It bursts a little plastic disc, and the fire comes out and catches the powder on fire. Then it burns at a known rate. This bullet is pressed tightly inside the cartridge, and so you get a certain amount of pressure build up inside the cartridge, and then it shoots that bullet out. It goes through the rifle. In order to make it more accurate, it spins the bullet. So you can see rifling marks inside the barrel. I've always wondered how they do that, and I have a friend who's a gun enthusiast, and he talks about them putting a plug inside the barrel that's made out of harder material than the steel that the barrel's made out of, and they pull that out through the barrel, and they basically deform the barrel and leave behind areas where it's not deformed, and so the rifling is just pulled through. Now you can get other kinds of ways to rifle the barrels, but they pull it at a certain twist rate, like so many twists per foot. And so the more twist rate, the faster the bullet spins, but the slower it comes out because there's more drag. So it's a trade-off for accuracy. So that's a cartridge. And then here are the top 20 guns seized in 2014 by Chicago police. I just found this fantastic graphic that shows you all the different types and sizes. Okay. And so you've got all kinds. You've got full size, semi-automatic. What does a semi-automatic mean? Well, that means every time you pull the trigger, a cartridge is spent. Okay, a bullet comes out. None of these are fully automatic. You could make an illegal gun by making it fully automatic. Okay, but it's not that easy. And so these are what we call semi-automatic. Now, a lot of these revolvers, okay, are called dual action. And what that means is when you pull the trigger, the first action is to cock the hammer back, and then you go past a certain point and it's released. So that's double action. And you've got a really long trigger pull. You're pulling, but they're sort of inherently safe because if the hammer's not back, it's not going to fire the round. And so a double action weapon typically doesn't have a safety, okay, because you have to cock the hammer back. Now, some of them you could cock and then have a safety. They make all kinds. But if you pull the hammer back manually, then it's cocked and ready to go. And then the trigger pull is really small and really light. And so that's a double action or dual action pistol. And just a bunch of different calibers. So you've got 45s. Here's a little pocket gun here, this 380. So that's probably the most common caliber for really small subcompact pistols. It's hard for like concealed carry. It'd be hard to conceal one of these larger pistols, these full-size pistols. The 380, the smaller ones, are much easier to conceal. Here's different rifles and shotguns. You've heard of the Armalite AR family. These are the Armalite rifles. The thing that makes these so popular is, in my opinion, these little Picatinny rails and all of the different accessories. Like this one has a bipod. It has a front grip. You can swap out the scopes. You unscrew a couple of screws and it pops off. You put it back. As long as you put it on the same rails, it's in the same position. It's very repeatable. So it's like, for the gun enthusiast, it's like Legos. You can mix and match and put different things on there. So that's part of what makes it so popular. This is that Kalashnikov family, the AK family. These are fairly inexpensive because, I mean, this frame right here can be mass produced out of sheet metal almost. I mean, it's kind of a flimsy construction, but again, can be made very inexpensive. Still, for some reason, still a very robust system. The deer rifles, quote deer rifles, hunting rifles. This would be a bolt action rifle where you have this bolt, you bring it up and pull it back, and put another round in the top, or you can have a magazine on the bottom that will feed the next round in. And then the different shotguns. You have a pump action, you can have semi-automatic shotguns where you load 3 or 4 rounds in this tube, and then as you shoot, the gas pressure will throw the bolt back, and another round springs up, and then when the bolt comes forward, it'll load the next round. So all the semi-automatic rifles do something similar. The explosion, before that bullet comes out, there's a return gas tube, and so that pressure is enough to blow the bolt back. And then there's a spring-loaded magazine, and it puts the next round up a little bit, so when the bolt comes forward, it grabs it and slides it into position. So you shoot once, it ejects the round and loads the next one. You have to release the trigger and pull again before you shoot the next one. So an automatic weapon would be you pull the trigger and it loads the next one and then it releases the firing pin. And so as long as you've got the trigger down, it will just keep shooting. But if you have a semi-automatic, you have to release the trigger and then pull again before it shoots the next round. Now, what's interesting is in order to define the guns, this is the trigger mechanism and the thing that holds the magazine, and that, according to the Bureau of Alcohol, Tobacco, Firearms, and Explosives, commonly known as the ATF, but it's BATFE, defines this as a gun. So that's the gun. You can buy the barrel, you can buy the upper receiver, you can buy the stock, you can buy the pistol grip, the scope and everything. But if you don't have the trigger and you don't have the magazine holder for the bullets, you don't have a gun. You can have all of that stuff. None of that other stuff is serial number stamped. It's not serialized. But this is serialized. Now this piece right here, they've got, you can 3D print those. Now that's, this is just the current situation we're in. There's plans on the internet that you can download and 3D print that. It's kind of bulky because you need the plastic to be heavy duty. But this thing right here only contains the trigger package and the magazine holder. It really doesn't handle any kind of pressure. So a 3D printed lower receiver is totally valid. It totally works because all the pressure is up here in the upper receiver and the barrel. So the steel parts are not serialized, but the lower receiver should be serialized. Now, if you 3D print your own lower, you have what they call a ghost gun. So it's a gun according to the ATF, but it doesn't have a serial number. So you may hear that term. I think President Biden said a few months ago, he was talking about getting these ghost guns off the street, and people were like, what's a ghost gun? That sounds mysterious, but that's what they're talking about. It's a lower receiver that has no serial number because it wasn't manufactured by an arms manufacturer. Okay. So any of these lower, you could even, I guess, I don't know, this isn't as modular, but if you had the lower receiver on any of these other pieces that you had somehow made yourself, then that's so-called a ghost gun. Now, is that illegal? Well, it's not illegal yet. I mean, we have essentially the right to produce our own firearms. We cannot produce them to sell. So if you were to make one of these and sell it, like if that was your intended purpose, then you'd be in violation of the law. If you make one for your own personal use, you're not in violation of the law. Possession is not, at this point, illegal. So it's just a little bit of information on these different systems. Any questions on this? Because this is a very current topic. No? Any question on the cartridges or any of these other things? Okay, so let's get into the evidence. So some of the constituents of the primer and the gunpowder that we detect with gunshot residue would be these top three metals: lead from the lead stiffnate, barium from this oxidant that's mixed in with the gunpowder, the barium nitrate, and then there's also a fuel. Sulfur burns pretty well with oxygen, and so antimony sulfide would be a fuel. The sulfur would burn, and that's going to produce molten bits of metal that contain barium and lead and antimony. So now, I mean, of all these years in chemistry, you probably didn't really talk much about element SB. Today is SB's time to shine. So antimony, or stibnium, is what the Latin name, but antimony, SB. And so that's, if you find all three of those in an elemental analysis of gunshot residue, then you've confirmed it's gunshot residue and not like a campfire. Somebody was like cleaning up a campfire and got soot or something on their hands and you test it. If you don't see those metals, it's not classified as gunshot residue. And then you have the gunpowder, the nitrocellulose and nitroglycerin. You might still have trace amounts of those pieces inside the gunpowder. You might have stabilizers like diphenylamine, ethyl centralite, methyl centralite. And then they can put in dinitrotoluene as a flash suppressor. Why would something explosive be a flash suppressor? And that is an interesting thing. The gun only flashes if it's still burning, if the material's still burning after the bullet leaves. So if you can get it to burn faster, you build more pressure and you get a more complete burn, and so you have lower flash. So if you're at night and you see a pistol shoot, you see a huge flame come out of a pistol. You see a longer rifle shoot, you see less flame many times, because most of that powder is being burned before the bullet leaves. And then plasticizer, like I said, these little prills of propellant are engineered. And so in order to keep them from becoming too dry and breaking apart, they'll put polymer in there and bind them up with a polymer, and then they'll put a little plasticizer to keep that polymer flexible. So that increases the shelf life of the ammunition. So does the stabilizer. So these are all trace elements. So if you end up with a trace element analysis, these would be some of the things that you would look for. Here's the little cloud that comes from a revolver. Revolvers are some of the most dirty pistols that you can have. It's easy to see on my screen, but this is sort of the cloud that is on this person. So this is all of the smoke coming out, and inside that is the unburned and some burned material from the cartridge. And so it's going to look how much is going to get on her wrist and on her hands. Okay, a lot of it's going to be on her wrist and hands. Okay. And so this is where the gunshot residue is most often swabbed, is the top part of the hand. And so they'll swab that and test to see if that person has gunshot residue on them. Here's a good picture. This is actually a fantastic picture. This is a revolver. And again, you see, because there's this break in the revolver between the cylinder that holds the cartridges and the barrel, a lot of gas and hot stuff leaks out of here. With that hot expanding gas, it's a lot of noise. So these are loud weapons too. The revolvers are incredibly loud compared to a rifle. And what a cool picture. You can actually see the bullet coming out here. So that's such a cool picture. So there's the bullet. And you see all of these little traces. Those are the molten metal and burning particles that contain lead, barium, and antimony. So that's really what we're going to be looking for in terms of our gunshot residue. So they swab the hands. They can also look at the entrance wounds to sort of estimate the firing distance, and they can determine whether or not the person has discharged a firearm or whether they were in a close vicinity of a firearm being discharged. Mostly the hand is what they analyze. Here's an entrance wound, and look at all the charring. So this was an up-close shooting because of the charring. All the unburned gunpowder actually got on the clothing and burned it, and it charred the clothing. And so that's we could test that just to confirm that was gunshot residue. So there's different kinds of color tests, like the Griess test or the rhodizonate test, for looking for nitrates or lead. Then there's instrumental analysis, swabbing that area, looking at it under scanning electron microscopy, or looking at atomic absorption. Now, high dollar and very rare would be neutron activation analysis, but I mean, if it's a high profile shooting, the neutron activation analysis is going to give you a % composition of your sample by every element on the periodic table. So they've got the cross sections for every element with neutrons. They hit them with neutrons, and it makes the nucleus unstable, and it will spit out a gamma ray that's characteristic of that nucleus. So it's kind of like a fluorescence measurement, but in the nuclear region. And so, and it can tell you by the number and types of signals that you get, the number and types of elements you have in the sample. But it's ridiculously rare and expensive. So you will probably never see that, but it's like at the national laboratories. If there was an assassination of the president or something, they would pull out all stops. Every government agency would do what they could to contribute to that analysis, and they would probably pull out something like that. X-ray fluorescence and ICP. This is going to be for trace metals. The atomic absorption spectroscopy is also trace metals. X-ray fluorescence is probably trace metals too. They don't even really look at carbon with our X-ray fluorescence. I mean, you can detect it, but it's all down. The first two rows are just sort of treated as noise in terms of X-ray fluorescence. And so it's really anything above the second row. So starting at sodium and going higher, that would be what you would use X-ray fluorescence for. And now also this dispersive X-ray analysis. So these are all looking for that lead and barium signals. The organic components, you would use HPLC, capillary electrophoresis, and GCMS. So this is. Did y'all do electrophoresis in biochem? Yeah. This is the same kind of thing. You're separating things based on charge, but it's in a capillary. And so you have your you have this tube, and you put a couple of electrodes in there, and the tube is filled with an electrolyte, and then you inject your sample and turn on the voltage, and the cations or the anions run to the other end, and in that electrolyte, and it will drag even neutral species along with it, and it's a repeatable signal, and so you will get repeatable signals for things, and it's super fast. So you can say, well, how is it better than HPLC? Well, it's faster and repeatable, kind of like IMS. It's sort of low tech, and you get really good results. Let's look at some of the color tests. The modified Griess test. So back in the day when we didn't have digital cameras, we had things called photographic paper, which has an emulsion on it. So they could take desensitized photographic paper and they make this up with this naphthol solution, and they put the evidence question side down on the gelatin coated side of this photographic paper where the slurry is. And what they're doing is they're transferring the nitrates and nitrites and so on into that gel, and then they peel it off, and then they spray a developer solution on it. And so they see sort of a mirror image of the questioned item, which would be like a shirt, or in this case a trench coat where there's an entrance wound. They put that gelled paper on, they peel it off, and so they've had a transfer of the evidence onto this gelatin, and they spray a developer. And so here's an example. So you've had an entrance wound, you've got gunshot residue, they stick this sheet of paper on there, peel it off, and then spray it, and you can see the color change. And those are where the nitrites are. And so they're detecting that. The sodium rhodizonate test tests for lead. So you can spray the questioned area. So if there's a shooting here, you spray that area with this sodium rhodizonate and distilled water, then spray it with tartaric acid and sodium bitartrate, and then spray it with hydrochloric acid, and so then you see color changes. So you see a pink color and then a blue-violet area, which is a positive test for lead. So here's the Griess test on the left, the sodium rhodizonate test. You see the entrance wound there. You're spraying the solutions on the garment, and you're seeing the color changes. So here's another photo from a former student, Joe Trevino. And so he's working, he's changed jobs now, but he was with the Garland Police Department. And these were some evidence photos that they had. And so here you see the purple and pink from the rhodizonate test. You see the nitrites in the Griess test. So there's the pink, and the hydrochloric acid makes it go to blue-violet, and so you see the purple. And then this bottom left one is just charred fabric. You can see the charred area. Now, in terms of collecting evidence, you're going to have, again, the photography, but a lot of the chemical reactions would be considered destructive tests. And so, and then on hands and clothing of subjects, you have these swabs and tapes. And so here's some example of the swabs. You know, we use some of these things for like the COVID tests, where you had a little swab with this little plastic container on the end. I thought that was pretty neat to get to see some of these things, but they have the same kind of deal. You have the container that's going to keep the evidence clean from the environment. So you swab the area, you pull it down into the container, you close the lid, and then you snap the stick off. And so and it's just ready to go. Then they can take that into the lab. They can extract that with a solvent. So they'll put a solvent in there and extract that solution off the swab and then go and analyze it. Here's a little foam rubber swab. Again, this would collect particles because the particles would get entrained in this foam rubber area. And then it has a little cap that screws on, and this says left and right. On the little evidence tags would be like left and right hand, so they could swab the left hand and cap it up, swab the right hand, cap it up, send that in. This penny is there just to show you how big it is. Okay. And then I guess somewhere, I mean, it's way cheaper than that neutron activation analysis, but still an expensive technique would be the scanning electron microscopy. So this may not be something that it's certainly not something a local police department like ours would be able to afford. But if you have like a forensic analysis lab, let's say for the state or something, they might have scanning electron microscopy. It's not just useful for gunshot residue, it's useful for a lot of things, but this is one of the techniques that is nice. You can image the particles that you get, and then you can analyze them for their trace elements. Okay, so this is the sample chamber right here. So the samples go in this area. These little micrometer adjustments can adjust the tilt of the sample, you know, can move it around left and right so that you can get the image all in there. It's kind of like a microscope. You move the stage left and right. These controls are all up front. Now, a lot of these too will have motorized stages inside, and so you can do that on the computer too. So these are probably, you know, gross adjustments, and then inside the computer you can move it around. Up here is the electron source, which we'll see in a second, sort of the breakdown of this thing. So this is the electron optics. It sounds strange. It's not light, so why we call it optics? Well, we can adjust its focus using electric fields. So it's very similar to having lenses. If you have a beam of electrons going in a columnar line and you have a ring that's charged negative, you're going to pinch that beam, just like you would a lens. And so the math is the same. We can expand and contract that beam, and we can move it around on the sample using electric fields. Just like we use the refractive index of lenses, we use electric fields to steer that electron beam. And so they just call it electron optics, this little electric field manipulation areas. And so then it's focused on the sample, and then the sample we'll see in a second, you'll see the electrons, they come off the sample and are detected. But it can also emit X-rays, and so X-rays can go up this tube and hit this detector up here, which is liquid nitrogen cooled. So this thing up here is a liquid nitrogen doer. And so in our place, we had a little step stool beside us, so you could climb up the step stool to refill the liquid nitrogen, but I don't see the step stool. And so these X-rays are detected, and let's look to see where those X-rays come from. We'll see that in a second. So here's the electron optics. So the electron beam, you know, what is an electron gun? Well, it's not anything super special. It sounds really cool. It's just a wire that's really, really negative compared to the sample. And so the sample can be held at ground, and you have a really negative wire, and to the wire's perspective, ground is very positive. It's much more positive than that very negative wire. And so it's attracted to ground, and it'll start just boiling off. If you think about electrons, they don't like each other, so they're on the surface of any conductor. So if you have a wire that's conducting electricity, the electrons are on the outer surface of that. And if you really make it negative and you have a lot of current going through, it's like a traffic jam. And when it sees ground, that's like being on 45, bumper to bumper, and you see over here where the grass is kind of beat down, it looks pretty solid, and it's not muddy, and you're like, I'm going for it, I'm cutting off. And so that's what the electrons are doing, is they're seeing ground, and they're like, all right, I'm going. And they go. They leave the wire, and now they're flying through space towards ground. And then we can steer them with these lenses, these positive and negative lenses. Now there's deflection coils too, and we can steer that beam left and right, X in an XY manner, and so we raster those electron beams across the sample. And at every point, those electrons hit the sample and knock off secondary electrons, and those hit these detectors. So if it's hitting a place that has lots of electrons, like a metal, then the electrons are streaming off that metal. Then if it hits a conductor where there's not a lot of electrons, then it goes dark. And so you can scan across the surface, and the metals are bright. They give lots of secondary electrons, and other places are really dark. And so you get a black and white image. You just stream that beam across the top, and you get a black and white image. So the electron beam hits an atom here. Okay. This electron beam hits this atom, and you can see it coming through right here. And the atoms closest to the nucleus are actually easier to hit. I know that seems contrary to what you might imagine. But if you think about the probability of that electron being in a given spot, the 1s electrons are in the same spot most frequently, whereas the ones way out on the 3s, the 4s, the 5s shell, they're spread over, probabilistically, they're spread over an enormous area. And so it's most likely to hit one of the 1s electrons. So you spit out a 1s electron, and now that atom is positively charged, and I like to think of it as musical chairs, but in rows, right? The 1s being close to the nucleus is a primo spot. And so one of those outer shell electrons jumps down into that empty seat in the 1s shell and spits out a characteristic X-ray. And every element having a different number of protons has a different X-ray that's spit out when something drops into the 1s shell. So this tells you exactly what you have on the periodic table. So every element on the periodic table will give you a unique X-ray fluorescence signal. And so then that's detected by that liquid nitrogen cooled detector, and you can just basically tell what elements are there. So this is the sample that you get from an energy dispersive X-ray scan. You see it does go down to oxygen, which is on the second row, but anything below oxygen is just thrown away. So they're not looking at the amount of carbon, nitrogen, or anything like that. There's so much carbon anywhere anyway on every sample. Think about Sam Houston. We're in the middle of the forest, and those trees are spitting out what they call pinings. All of these organic molecules are just coming out of these conifers, and they're landing on everything. So no matter how clean you think your evidence is, it's sitting in a bag. It's coated in these pinings and plasticizers from the bag, and so the carbon is not going to really tell you anything. Everything's going to have carbon on it. And so what we're really looking for is these confirmation elements, this lead signal, antimony signal, and barium. Now, notice they're color-coded. See the lead, it's got a couple of peaks here. Antimony is red, it's got 3 peaks. Barium's got 4 peaks. Why is there not just one peak for each element? No, that's a great answer, though. But this is thinking about this particular mechanism for X-ray emission. Think about the different orbitals. So you got the 1s, the 2s, and 2p. Then maybe you have out here a 3s, and a 3p, and a 3d. Most of them are by the principal quantum number. Okay, and so look where barium is. Man, it's way down there. Let's see, right over here by cesium. You know, it's the 6s. And so you have all of those outer electrons, and you've got a bunch of elements there. Some of them, that missing chair in the 1s orbital is filled by a 2s electron. But then this atom, it was a 3s electron. And that atom, it was a 4p electron. And so you get different peaks based upon all of those outer region orbitals that are filled. And so that's why we have all of these different ones. Now, lead also is very big, but it really shows only a couple of peaks for the lead. You see the probability really drops off. And so the largest signal is going to be from the adjacent orbital. So the 2p orbitals are going to drop down into the 1s. There has to be a change in angular momentum. So it has to go from like a p to an s from the selection rules. And so that's going to be the biggest signal, like the 2p down to the 1s. Is going to give you that first signal, the biggest one. Now here's the pictures so that you get from the SEM. The EDX analysis tells you the types of elements, and you see these round molten particles that are really bright. Okay, so let's see. So we're right over here. Notice how it's irregular in shape, and it looks like it's been melted. Kind of looks like a lava rock, right? Now some of them are not that irregular, but you see some little bumps on the surface, but they're not in a perfectly repeatable pattern. Okay, so when I say irregular, I'll compare it to pollen, and you'll hopefully see what I mean by that. Some of them are molten, but then they're missing stuff in the middle. So it might be like a molten core which had some unburned propellant on the inside. We don't really see the unburned propellant because it's carbonaceous, and the electrons are not generated by that substance. So we're getting most of the electrons from the metal oxides. Okay. And then these two are very irregular in shape. So these are what I'm talking about, irregular in shape. Let's look at some of the false particles that could be mistaken as gunshot residue, and that is pollen grains. They're about the same size. This is what's in my nose right now. It's driving me crazy, in my eyes, right? This is all of this pollen that our trees and plants are putting out. Look how regular those are. And these cannot have been burned or molten. Why would these not be an example of molten particles? What if let's say this was made out of metal, and let's say I heated it up? What would happen first thing? What would deform first? The spikes. The spikes. Those spikes tell you these weren't molten. Okay, because I mean, think of a snowflake. What happens to the snowflake? The spikes start to melt first. Okay, and so these pollen grains, that's really how you determine this surface structure is evidence that these weren't molten. Now this one, you know, that might look like it might have been molten, right? It kind of looks like this down here in the bottom right. It doesn't give as bright a signal for secondary electrons, and it is exactly triangular. Okay, so that makes it less likely that it was molten. It's perfectly triangular. And so that would be the only particle that I would want to hit with the beam. So if I've scanned this sample, so I got this off of someone who's been shot, I got this swab or out their hands, I look at it in the SEM, I look at all this, I go, no, that's all pollen. But I'm going to put the electron beam right here. So I'm going to draw a little square with my software, and I'm going to say blast this area with electrons and send the X-rays up to the X-ray detector to see what that particle is made of. And I would not see barium or antimony or the lead. And so I would say, no, it's negative for gunshot residue. Okay. So you image it first, you look for those bright particles, then you tell the electron beam, hit that particle and tell me what it's made of. It's pretty cool analysis. So I love SEM EDX, but it's just expensive. But if you do get into a lab that has that, that might be one of the areas that you specialize in, and then you could be the person in charge of running all those samples. You'll have a backlog. You'll be doing this day in and day out, taking images, writing your reports about whether it was GSR or not, or whatever kind of evidence questions you have. So this is sort of in words: rounded, non-crystalline, irregular molten particles, 1 to 10 microns in size, containing barium, lead, or antimony. If and those would be confirming GSR. If they're just 2 of the 3 particles, you would say it's commonly associated with GSR or characteristic of GSR. Now, here's some interesting things: that the presence of gunshot residue can't determine whether the victim's death was a homicide or a suicide. And according to Joe Trevino, he said that they won't even run the sample. So if it's just a single person and there's a gun in the room, they're not going to run it because it's not tying them to an interpersonal crime. You know, it can't be used to distinguish between shooters and bystanders. Okay. They'll only run GSR kits involving crimes against persons. So you've got a homicide or attempted homicide. Someone took a shot at you and they were held at the scene. Then they'll do it. They'll swab that person's hand to verify they were the one that shot the weapon. And then, so that if you get a positive test, it's just consistent with that person having fired the weapon or been in the vicinity of a fired weapon or having touched an item with gunshot residue on it. So it's a pretty general, positive test doesn't tell you that much. And there's also ways to get away from the positive test. If your hands are completely coated in other kinds of soils and you lose the signal of the gunshot residue in a bunch of other residue, you got, a mechanic in a garage who's got grease up to his elbows, and you swab that hand, it's going to be buried in a sea of other contaminants. Let's say he works on, disc brakes or something like that, and some of the particles from the disc brake work are going to be on his hands. Again, it's going to swamp the signals, give you all kinds of trace metals. Of course, people washing their hands or wearing gloves, etc., would cause a false negative. Okay, sometimes organic testing is positive. Sometimes the ammunition doesn't have antimony, antimony sulfide added to it. And so they're trying to remove some of these toxic elements from the ammunition, primers and bullets. And then here's some other sources of false positives. Okay, this is a stud gun. Also, sometimes there's one famous. It's called a ram shot. It's like a pistol. This one just has a straight handle. You load these little 22 cartridges in there. Notice that they're crimped on the end. Okay, so they're using the brass cartridge, the rimfire, and the propellant to drive a nail into concrete. So it's pretty neat. You load that nail in the end of this gun, you put a cartridge in there, and you have a 2x4 where you're going to put the studs on a house. You have a 2x4 there, and you bang it down, and it'll drive that nail through the stud and into the concrete. And then you load up another one, pow, and it's great. I mean, it's a one-shot deal, and it'll anchor that wood into the concrete. Well, that's giving you gunshot residue. So that could be a false positive as well. You could be, it would have gunshot residue, but it wouldn't have been in an interpersonal crime. And so then from explosive detonations, this is sort of the same kind of process. We've got combustion, we've got incomplete combustion. What kind of trace evidence do we have from those things? Here's the trace in terms of the capillary electrophoresis. And so here's a lot of the, we've got nitroglycerin and trinitrotoluene. So these are some of the formulations for the propellants here. Let's see, here's the dinitrotoluenes here. So these are unburned propellants. And then these three, let's see, I guess all of these others here are trace organic compounds, and they are the stabilizers. So it looks like a liquid chromatograph or gas chromatograph, but it's just a different kind of way of separating. So capillary electrophoresis. And then they have a UV detector. Now, there's nothing about the UV that's going to tell you it's one versus the other. It's just based on calibrated retention times. So you just run your standards, and you know at what time these different things come out. Here's a picture of some of those plasticizers. All of these phthalates, so this piece right here is the phthalate piece. It's an aromatic diacid. Okay, and so then dibutyl phthalate. This is the butyl part, and it's di because there's two of them. Okay, then you have octyl phthalate. So again, you got some version of octane stuck on the phthalate piece. Here's a picture of camphor. So all of these different things are plasticizers. It's these arms right here that keep the polymer from crystallizing. So crystalline polymers are fragile. Non-crystalline polymers are flexible. We can engineer polymers. We'll talk about that later when we get to synthetic fiber chemistry. And these plasticizers keep those polymers flexible. Now, I don't know, maybe from your experience in inorganic, which you're taking right now, you think of crystal formation as being positive and negative charges, right? You've got oxygens, which are negative, and metals, which are positive, and you make this crystalline formation. It's very easy to see how a metal compound could be a crystal, right? You've got the little cube, and you've got things on the corners and things in the middle and things in the different spots, right? Polymers crystallize in a slightly different way. Polymers are always moving around each other, bumping into each other. They're very close. It's a solid state, but they're amorphous. But over time, they can zip together just like a zipper. So think about the CH2 groups. It's not that they're really attracted to each other. It's that they fit perfectly together. So think of a zipper. Each one of those little things in a zipper is not very strong, but you put them all next to each other, and then when they're zipped together, it's strong. So that's what's happening when the polymer crystallizes. You got the CH2 groups that are bumping around. They're not lined up, but over time, they start to line up. And you get two or three together, and then the fourth and fifth, it's easier and easier to get them to crystallize. That forms a hard domain in that polymer. And then when there's stress, the hard domain stays put, and it rips the polymer around those hard domains. Okay. So we don't want that to happen with a lot of our polymers. We want them to remain plastic and movable. So we put plasticizers in them. The plasticizers are the compounds that are controversial now because they, some of these can mimic estrogen. So they can mess with your endocrine system. And so you hear BPA-free, bisphenol alcohol. So that's another kind of plasticizer. And you have a methyl group in the middle. You have two aromatic rings, and then alcohols on the end, BPA, bisphenol alcohols. And those are the estrogen mimics. And so they're taking them out of food contact surfaces. Like they're taking them out of your Tupperware containers. And a big place where they were, which may have affected every one of you, and maybe even me, is they had them in baby bottle nipples. So thinking about that plastic, that needs to be pliable, and it is in food contact directly with an infant's, feeding. And that's a lot of exposure. And so if those bisphenol alcohols were getting into an infant, messing with their endocrine system, that's a bad deal. So they've taken those out, but that was a plasticizer. And so that's why we use those plasticizers. Stabilizers are free radical scavengers. And so if you've got this molecule here, let's take a free radical. So you have an R dot, right? So this hydrogen, not a proton, but a hydrogen can come off of there and quench that radical. And now what is going to happen with that missing valence? Well, then these electrons are going to drop down and make a double bond or whatever. So it's these nitrogens and oxygens, and basically we can take that free radical and delocalize it across these nitrogens and oxygens. So you see these nitrogens and oxygens next to methyl groups. Those are antioxidants. And so you have something that's a free radical in the body or in the material, mostly because of UV light exposure, and this will quench those radicals. Vitamin E does this in the body. So you see antioxidant properties of chocolate or coffee or whatever. It has a lot of these compounds in it, and it's supposed to help you with aging because supposedly these oxidative pathways accelerate aging. Then other physical evidence, you have the casing materials. There's typically a question I have about trace elements in the surface of like a full metal jacket. Let me talk about that a little bit because I think it's on the homework question, that if I've got a trace element on the surface of something, I could analyze it two ways. One would be to use a surface sensitive technique like X-ray fluorescence. Hit it with X-rays and look at the X-rays come on. That's great because the X-rays are hitting the surface and the fluorescence is coming from the surface. I could also take it over to TRIs and use their inductively coupled plasma. But to do that, I need a liquid sample. So I'd have to dissolve the whole bullet. Not a problem. I put it in nitric acid and dissolve the whole bullet. But if it's a surface contaminant, I've just diluted it with the mass of the whole bullet. That's the problem. And so the reason why a trace element on the surface is not something you want to digest and dissolve is because you're now diluting it by the bulk of the object that you're analyzing. If you have a surface contaminant, use a surface technique like scanning electron microscopy with the X-ray detection. Anyway, so just think about surface versus bulk. If it's a trace element in the lead of the bullet, then it's a bulk effect. And so I need to dissolve the whole thing and analyze it that way. But if it's a trace contaminant on the surface of something, use a surface technique to detect that. Then there's, again, if it's an explosive, what was the initiator? What was the detonator? And then here's where a lot of the evidence comes in these types of situations is the arming, fusing, and firing. Okay. Was it a circuit board, a watch, a cell phone, a kitchen timer? Very few of those things are destroyed by the explosion. So you have the detonation. You may do some trace analysis and say, okay, this was like composition B or a nitramine explosive. Okay, great. You know what the explosive was. How was it set off? And you're going to look around at the source of the detonation and try to find the evidence that's left behind. Go ahead and watch this video on your own time, this research firing site at New Mexico Tech. If this part of the course really excites you, maybe that's a great place for graduate work. They have a firing site. They do a lot of work for the FBI, Department of Energy, Department of Defense, where they actually blow things up. And so they have an area where they'll make a car bomb and they'll detonate it and they'll look at how much destruction there was, but also they'll go back and look at the evidence, what was left behind. You've got all the car parts. Can you find the arming, fusing, and firing? Can you find what set it off? Was it a cell phone? Because there's evidence there that might tie you back to the perpetrator. Okay, so we're good. Any questions about any of this stuff? I think this area is interesting, obviously. I get pretty excited with it.